I'm Rohit Kumar Singh, the TA for teaching assistant for this course of statistical mechanics, and this is the eighth live session. And this course is being taught by Professor Dipanjan Chakravarti over the NPTEL portal. So I hope you guys are following the lectures there. So the goal of this live session is to recap the concepts uh, that are already being discussed in the lectures and try to solve some sample problems to help you with the tutorial assignment. And you can ask anything in between. So you can just unmute and ask if you have any doubt. So let's for the past 3-4 weeks we've been discussing the statistical mechanics, starting from the concept of ensemble, and we've seen that there are three types of ensemble: macro canonical, canonical, and grand canonical. And the three types of ensemble applies to different kind of system. So the grand canonical one is the most generalized ensemble, where we allow the exchange of both energy and particles, right? But in all of these we have not included the interaction between the particles of the system, right? We just uh, we just assume that they are non-interacting in all the potential energy, sorry, in all the uh, Hamiltonian that you have seen. We kept the potential energy, interacting potential energy, to be zero, uh, right? But that is not the case. I mean, that is true for ideal gases, but uh, that is not the case for real gases or real systems, because they might be interacting, right? So for the cases where systems have a large number of particles and they are interacting, uh, we need to modify the partition function uh, for those kind of systems. So th- we can take the simplest case of uh, a single component system. So a gas with only one type of particles, okay, a single component. Let's keep it classical. So classical and monoatomic gas, okay. And the Hamiltonian for such a system will be given by this formula. So this is the kinetic energy term. Sorry, Vikramadit, can you mute yourself? Yeah, okay, thank you. If you have any question, you can unmute and ask, but otherwise, please be muted. Okay, so the Hamiltonian for such a system having a single component and monoatomic gas is given by this formula. So this is the kinetic energy term of all the particles, and if we are uh, assuming interaction between the particles of the system, then we'll have to introduce a term of interaction, right? And the simplest case will be to use a pairwise interaction. So we will assume that all the particles of the system are interacting with all the other particles. So so there is a pairwise interaction, okay. And this I and j, they can be, they are just indices over n particles of the system. So here uij is basically two particle interaction, okay, and it is summed over all pairs. So how many pairs there will be if there are n particles? How many pairs there will be? There will be n minus 2 by 2 pairs, right? Is it fine? So, and this interaction energy, the uij, this depends on, basically this will depend on the relative distance between ith and jth particle. So it will be dependent on the distance between the two. So if the two particles are very near to each other, so suppose this is the system. So if two particles are very near, the interaction energy will be high. If they are far away, it will be low. So that is what we expect from a simple electrostatic interaction. Yeah, Pravati Nayak has raised his her hand. Can you tell me if you have any doubt? You can unmute and ask if you have any doubt. Okay, I guess it's just by mistake. Okay, so yeah, so this is the general case. Okay, now how will the partition function be modified for such a system? So last week we saw that if we have a classical system, the partition function for such a system is given by, so this is the canonical partition function that we are talking about. We can generalize this to grand canonical by using the fugacity term, but let's just write the canonical partition function. So for a classical system, the canonical partition function is given by this formula, right? Okay. This dw is the uh, volume element in the phase space. So this is basically, you know, three. Sorry, let me. Mhm. So the volume element is given by this 3n p and 3n q, or here we can keep it, since we are using the r coordinate, we can keep it 3n r. So this is the partition function for a classical system. And now we can put this Hamiltonian inside this formula, and that will give us the uh, partition function for a interacting gas. Okay, so let's quickly do that. uh, so let me know if you don't understand any step. Okay, so I'm just on the I'm just putting in the Hamiltonian in this our formula. So minus beta sum over I pi square. Okay, and then minus beta sum over uij, bracket closed, 3np 3nr. Fine. Now you can see that we can integrate over this momentum space, right? Because it is just exponential of some constant and then p square. So it's an integral like this. Sorry, it's an integral like this, some beta p square dp, right? No, dqp. And then for the volume element we can, so dqp we can write 4 pi p square dp, right? And we did this kind of integral in the last lecture. You can go and check. So what we found was the integral for, I mean, this kind of integral gives us uh, so then, okay, so then we'll have p square, some constant p uh, minus some constant p square on the exponential, and then dp. And this can be integrated using uh, you know integral by parts. Okay, so this I did last time in the last lecture. You can go and check. So I'm just going to write the result directly. And yeah, so the integral over the momentum space will give you, so these terms are there, it will give you 2 pi m, okay, beta to the power 3n. And we are left with here only the integration over the position coordinate. Okay, so which is minus beta uij d cube r 3n d to the power 3n by r. Okay, and so we write this as in a compact form. We can write this as lambda to the power 3n. So I'll tell you what lambda is, and then uh, z n vt. So here lambda is given by this formula. So I've combined the h and this term to have a constant called lambda. Okay, oh, this is 1 by 2. So this is called mean thermal wavelength. Okay, now why it is called a wavelength? Because you see the dimension of this thing, it is the dimension of wavelength, right? You know, the in quantum mechanics the wavelength is given by h over p, right? And so this denominator has a dimension of momentum. So this h over this term is called wavelength. Okay, it is called a mean thermal wavelength. So this term will come again and again in the construct. I mean, in later in the course also. And the other term, which is Zn, is just the integral over the configuration space. I mean the position space uij. Okay, and this you can write also as so this is the sign of multiplication, right? So you can take summation into multiplication because these are exponentials. Did you get how we went from here to here? So basically we have something here like e to the power minus beta sum over uij, right? And so if you expand it, it is simply beta u I mean, so u1 2 plus u2 3, and these terms like this. And this you can write as beta u1 2 into minus beta u2 3, like this. So this is just a multiplication of all these terms. right? So that's how we get this. So it makes calculations easier, so that's why we have written. So this integral is called configuration integral, and this is the partition function for an interacting system. Okay, so you see that the partition function for interacting, I mean for a gas which is single component, classical and monoatomic, it just depends on it just depends on this configuration integral. Okay, which in turn depends on this interacting potential between the pairs of the particles. So this is a very simple case. You can generalize it later, but that will make things complicated. But you can assume. I mean, so for all the general purpose, like many, you can generalize many real system into such a system which has pairwise interaction. Okay, and the interaction is dependent on the relative distance between the particles, as we assumed here. So for these systems, there is something called virial expansion. So I'm not going to derive it. So we saw that whenever we have a partition function, you can you can calculate pressure, entropy, and such things. So similarly, for this kind of system, the pressure is given by so you know that for ideal gases, pressure, the equation of state is given by this formula, right? For ideal gases which are non-interacting. But if you have a interacting system, then this is no longer valid. Okay, so and the most general expression will be something like this. So I'm just going to write it, and I'll explain what are the terms here. So b1 plus b2 n by v, and then b3 n by v square, and then you have higher order terms. Okay, now if you look at here, if so b1 is equal to 1 always. Okay, and b2 is the second virial coefficient. Okay, and it is given by this formula. So let me write this: 0 to infinity minus, so this is the interaction potential ur minus 1 and r square dr. Okay, and then right now we will ignore the other. So there is a general expression for bl, uh, but I mean b2 is enough for us right now. Okay, now this if you look at, if this is 0, I mean if the interaction sorry, this is 0 when ur is 0, right? And so you are left with only b1, and b1 is 1, so you get back the the expression for ideal gases, right? So when we close the interaction, when we turn off the interaction, we get back the ideal gas case from here. Okay, but this is the most general expression for equation of state of a gas. Is that fine? Do you guys follow? Okay, thank you. Okay, so I'm not I'm not going to bore you more on uh, writing more equations and concepts. So let's go and solve some problems, and we will see. I mean, if anything comes up, if any new term comes up, I'll try to explain it, and we will use these results to solve some problems basically. So okay, so let's go to our first problem. Okay, so yeah, okay, so this is a problem on what we have discussed just now. So consider a gas of hard spheres, okay, which do not interact at all unless their separation is less than A, in which case the pairwise interaction energy jumps to infinity. Okay, so now uh, this is interesting. So here what the question says is that the gas is basically non-interacting, but if their separation uh, get below some distance a, then the interaction energy jumps to infinity. Okay, so this is the most ideal case, right? So if you have, suppose, two particles of the gas, okay, they will not interact unless their distance, so suppose the distance from the center falls below a. So this means that if they are interacting, they must be interacting like this. Okay, and this is the distance, so this distance uh, between their center should be a or something. So this is the case with hard spheres, right? If they will collide, uh, they can no, I mean they can no not move further into each other, right? They are hard spheres, so uh, so the interaction, so the potential energy basically goes to infinity. They can no longer come more closer because they are hard spheres, right? So so this is what this problem says. No, no, uh, the first problem is what is the average energy of such a system. Okay, so one way to calculate this average energy is to write the partition function, right? uh, yeah, write the partition function, and then from the partition function you can calculate the average energy, right? We know the formula to calculate the uh, potential energy, sorry, yeah, average energy of the system, which is given by this formula, ln of qn. So this is one way to do this, right? uh, I mean, you can so you can do this right away. So we have just calculated the partition function for such a system. So we will assume it non-interacting, because when it does interact, uh, the potential shoots up to infinity. Okay, so this is a gas of hard spheres, basically non-interacting. Okay, and so for such a system, what will be the so for such a system we have calculated the partition function earlier also, and it is given by this formula. You might remember. This is the volume of the sphere. Okay, and yeah, And so you can take the log of this. This will be so I'm writing the 1 by kt is equal to beta, so beta will come here, h square. Okay, this will be the formula. Sorry, this will be the log of qn. Sorry. Let me write it. E by n factorial 2 pi n kt by h square, and this is beta. Okay, so yeah, so this is one way to do this. And but yeah, but this will not work here somehow, because mm, yeah, this will not work here, because I mean we cannot just, you know, we cannot just ignore this term, because the potential energy is not zero, right? It is infinity, so we cannot ignore this term. mm, so then, yeah, this I mean we cannot calculate it this way, but there is another way to, you know, solve this problem. So let me try again. So we can solve this problem, uh, we can solve this problem using the equipartition theorem, right? So you guys know that for a classical system, you know, in the Hamiltonian, so if you have system, so if you have a classical system, so each quadratic degree of freedom, so this is a quadratic degree of freedom, the momentum. Okay, and there are three momentum, so there will be three quadratic degree of freedom, and it contribute to half kbt to the energy. So this is called the equipartition theorem, right? And we know that there are three, you know, degrees of freedom per particle. So uh, so the potential energy will be simply, and there are n particle, so the potential energy will be n into 3 into half kbt, which is 3n by 2 kbt. I mean, this is a simplest way to do this, uh, because I mean, in this way we will not have to consider this potential term. Okay, because we know that the potential goes to infinity at for some certain distance, and that complicates, you know, calculating the partition function and the derivative of log of partition function, right? So this is not a, you know, clever way to do this, but you can always use the equipartition theorem. This is valid everywhere. Okay, so the second option is the right one. Did you understand why cannot we use this formula? Because in the partition function formula, you see this term is there, right? And this and since the interaction potential is infinity, so I mean this complicate the integral. So we cannot directly, use this formula here. So that's why we use the equipartition theorem. So okay, I'll write what equipartition theorem says. So for a classical system, each quadratic degree of freedom contributes half kT or kBT to the energy. Okay, so this is the equipartition theorem, which is valid for all the classical systems. Now if you have a system which has, which is confined in a two-dimensional space, so you have just x and y, then the average energy will be just, 2 into half kT, so that is n kT. Okay, so for a two-dimensional system. Similarly, you can have a one-dimensional system and so on. But since here we have a three-dimensional system, so that's why we have the 3 factor here. Okay, further you can generalize this. If you have a system which potential energy depends on, you know uh, like this. So this is a potential energy of a spring, right? Or you have a harmonic oscillator. So then so x square and then y square. If you have such a system, then the degree of freedom will be like 1 1 1 1 4. Okay, so the average energy will be 4 into n into half kT, so you will have 2 n kT. Okay, so these are various different kind of scenario that you can think of. Okay, so I hope you understand to how to use this equipartition theorem. Is it fine? Okay, thank you. Now we have to calculate the pressure of this such a system. So we have the average energy, and we want to calculate the pressure. Okay, now for the pressure, uh, so for the pressure we can use the virial expansion that we saw here, right? This one. So we can use up to two terms, okay, in the expansion, and let's see what we get. Okay, so using the virial expansion, this is the formula for pressure. So B1 is 1 and B2 we have to calculate. There are higher order terms, but we will ignore these, okay, for now. And B2 we have to find out. So B2 I wrote is given by this formula. Okay, and here our potential is already given, so it is infinity if r is less than a, and it is 0 if r is greater than a, right? So let us put this inside this integral. So then your b2 is minus 2 pi. So let's first go from 0 to a, right? So if your u is between 0 to a, this is basically infinity, right? And then you have okay, so then you have from a to infinity e to the power, and if it is greater than a, then it is 0, just so e to the power minus 0 minus 1 r square dr. Now this is just so this will be a 0, right? Exponential of minus infinity is 0, right? So you will get minus 1 r square dr, and this will be 0, right? Exponential of 0 is 1, so 1 minus 1 is 0. So this is what you are left with, and so minus minus plus 2 pi r square, uh, 0 to a r square dr, it is just a cube by 3. So 2 by 3 pi a cube. Okay. So finally, your pressure, sorry. So finally, the pressure is given by N kVt by V 1 plus 2 pi a cube by 3 V N. Okay. So this is the pressure of such a system. Okay. So you see that this is not the pressure that you I mean, this is not the ideal gas pressure, right? The ideal gas pressure, you guys know, it is given by N kBT by V, just it has this extra term. Okay. So so this system that we are considering, it is not a ideal gas. Okay. Okay, so yeah, let's go to the next problem. Is it fine? Everyone understood this? We just use the virial expansion, and we use the expression for the potential, interaction potential, and we got this formula for the pressure. Okay, then let's go to the next problem. Oh, sorry. It here it is asking what B2 is, but we already calculated it, right? It is 2 pi a cube by 3. So second option. Okay, so then let's move to the next question. Okay. Now here there is a equation of state for a gas called dietary gas is given. Okay, so this is a equation of state. So like for ideal gas we have PV is equal to NKT. Sorry. So this is for ideal gas. Similarly, this is a interacting gas, special type of gas called ditracy gas, and the equation of state for such a gas is given by this formula here. Okay, so here V is the small v is just the the volume over number of particles, so V by N. Okay, and all other terms are A and B are constants. Okay, so the question asks here, at the critical point, what is the ratio PV by KT? So what is the critical point? Anyone knows? Have you guys heard about critical point? So when ice melts, okay, and become a liquid water, there is a point, or so suppose you are boiling the water and it is becoming a gas. Okay, so there is a point that the liquid phase and the gas phase become indistinguishable. Okay, and so there is no phase boundary, and this is called a critical point. So what happens at critical point is, so there are many things that happen. So suppose for liquid, surface tension vanishes. Okay, and then there are various things that happen, that compressibility diverges, and many things happen. But the most important characterization of critical point is given by this formula. So the derivative of pressure with respect to volume is 0, both the first and second derivative, they are 0. Okay, so this is the condition of a critical point. Critical point of a thermodynamic system. Okay, basically a hydrostatic system. So that's what we are considering here. Now in our case, we can we have the expression, we have the equation of state, relation between PV and T. So we can use these two critical point equation to find the this ratio. So let us try to find it. So let first we have del P by del V. Okay, so let me write first the equation of state. So P is KBT. So I'm writing it explicitly in terms of volume. Okay, so it will be P minus V minus NB, and one N will go here. Okay, e to the power minus A K KBT V, and N is on the numerator. Okay, so now this is written in terms of volume. Okay, and we want to find this thing. Now how to do this? So just take the derivative. Okay, uh, let us do that. So consider this A, consider this B. So first we'll take the derivative of this A function, and then for the B function. Okay, keeping the A constant. So like this, this is u, this is v, so we will do du by dv, keeping the v constant, and then we will do dv by, sorry, should have named it better, but this is a small v. Okay, now differentiating this with respect to volume, so this is small v here to avoid confusion. Okay, so differentiating this with respect to volume will give you in kBt b minus nb square, right? And then you have this term, and then again, so this term is constant, right, in both, but okay, let's write it anyway. And then you have the second derivative plus u. So differentiating this will give you minus na by kt, so this is the constant, and then 1 by v you have to differentiate, so that will give you minus 1 by v square, and then you have the exponential term. Okay, is it fine, or I have done any mistake? Let me know. Now you can combine all of this together, so you can take out na ktv n kt v minus nb, this you can take out, then you are left with inside the bracket v minus nb, so this is with a negative sign, and here plus, so this is odd, so you have na kt v square. Okay, and this is 0, so this term must be 0, right? I mean, either this is 0 or this is 0. Okay, so yeah, so putting this to 0 will give you a condition, I mean relating the v and kt, which is so let me write it, na kt v square is equal to 1 by v minus nb. So you will get a quadratic function of v, right, which is vna minus n square ab is equal to ktv square, so ktv square minus vna minus n square plus n square ab is equal to 0, right? And yeah, and putting this to 0, Yeah, this, I mean, this cannot be 0, otherwise v minus nb would go to infinity, right, which is not possible. So this is not 0. So you get this condition. So you get a quadratic equation for volume. Okay. And then you have another derivative, which is the second derivative of this function with respect to volume. This will be very tedious to do. So then I mean, okay, let me leave it as an exercise for you. So you if we take common b minus nb, that's what we did right here. Oh, or you want to, like, yeah, that's what we did from here. What else we can do? No, this is fine. This is fine. So you what you can do is I mean, you can again take derivative of, so you have, so you already calculated del p over del v here, right? So you can put this here and again take derivative as a function of I mean with respect to volume. So we'll get another very big expression. Okay. And then you can compare both the equation. So this is from the first order derivative, then you will have a equation from the second order derivative. Okay. And so what we want is this ratio, right, at critical point. And you see here that there is no I mean, the pressure is no longer in this equation. So mm, so yeah, at the critical point you will have to find some condition. Okay. Okay, I have the I have the solution. I mean, I have the end result. uh, I have not done the full solution. Okay. I thought it would not take so much time, but I think it will take some time if you want to do it. mm. So at the end what you will get is, so at critical point this will be equal to 2b, and temperature will be equal to this value, and the pressure will be equal to this. Okay, and if you take the ratio, everything will cancel, this only this constant will remain. So you will have to do the arithmetic. Okay, you will have to go through the full solution. uh, I don't want to do it right now because I might get stuck in between and we don't have time to go. I mean, we have more problems to do, but give it a try. If you guys won't be able to do it, then let me know. Next class, I'll try to solve it. Okay, it should be solvable. Just give it a try in your free time. I'll also give it a try. Okay, I have not done it yet, but at the end, this result you should get. Okay, this result you should get. Okay, so yeah, give it a try. Otherwise, in the next class, we will solve it completely. Okay, it's just you'll have to just do the all the arithmetic. It will be very long. It might you might get you might find some shortcut to do it. I've not tried it yet. I remember I have done it for the van der Waal equation of state, but not for this dietary gas. It is quite new for me also. But yeah, this should be solvable. You can just follow the procedure, and I think you will get this value. So I've written the end result. Okay, so just try to solve it and get this value. I'll also try it, and then we can discuss in the next class if you don't able to find it. Okay, so let's for now let's move to the next problem. So for the same system, the isothermal compressibility, okay, for the critical point, so V is equal to Vc, and as a function of T minus Tc. Okay, so difference in the temperature. uh, so we have to find the isothermal compressibility, and the hint is, so expand the del P over del V at the critical volume in terms of this temperature difference T minus Tc, assuming T is greater than Tc. Okay, so I think, yeah, this we can do. So we know the definition of isothermal compressibility. It is 1 over V times derivative of volume uh, with respect to pressure at fixed temperature, because it is isothermal. And this volume we can replace with the small v, which is V over n, because the n will cancel over on the numerator and denominator, so you can write it like this also. Now if you want to expand del sorry yeah, this is fine. So if you want to expand uh, so let's first expand the, I mean, to get the expansion of del P over del V, we can first expand the sorry equation of state itself. So we have P or we can write the pressure, so as an expansion of around the critical point, so using the Taylor expansion, so P is equal to P at critical point plus derivative of P with respect to temperature at fixed volume T minus Tc, and the other higher order terms. Okay, so now you can find this derivative, right, which is just the inverse of this. So if you take a derivative of this, uh, if you take a derivative of this and make it inverse to put here, so at the end you will get kt proportional to t minus tc, right? Because here it is in numerator, and then when you take a derivative and uh, take inverse of it, it will go over in the denominator, right? And yeah, so this also you can do. So if we do this around the critical point, so at the critical point, what is the pressure? So you see the pressure is constant, right? So this first derivative will be 0. So del pc del v, it is 0, and then you have del of del v del p over del t, right? And then t minus sorry we have t minus tc. Okay, now this is 0, then you have only this term, right? And at critical point, what is the formula for pressure? Sorry, yeah. So from here you can write P is equal to 2 to the power minus 2 kT by V, and then del P over del T is simply by V, right? You can put that here. So del over del V, sorry, 2 e to the power minus 2, what is this, kb by V, and you have t minus tc. Okay, and then you can take the partial derivative of this with respect to volume, which is just 1 minus 1 v square, and then you have the usual expression t minus tc, right? And finally you can yeah, sorry, okay, so then you have this at critical point is simply, so this is at critical point vc square t minus tc. Okay, and the vc at critical point is given by 2b, right? We found it here, so you can put the here, and then the isothermal compressibility, which is given by, sorry, yeah, which is given by this formula. Okay, so this will be finally, if you put everything, this will be b e square 2 kb t minus tc. Okay, This will be the final expression, which is the option 1. Yeah. This is fine, right? So what we did was sorry. Mhm. We used we expanded the pressure around the critical point, okay, and then we took the derivative with respect to volume, okay. The first term was 0 because pressure at critical volume is constant, so taking derivative as a function of v is 0. And then the second term, uh, we solved it, and we got this value, and then we just inverted it and put it back into the compressibility formula and got this result, okay. Okay, now is this fine? Let me know if you have any doubt. Okay, if it is fine, then let us go to the next problem. So this is the last problem for today, and this is a problem on a quantum harmonic oscillator, okay. So consider quantum harmonic oscillator with the Hamiltonian given by this formula, and here the p is the momentum operator, which is given by this formula in quantum mechanics, right? And we want to find the average energy of the system u. So how to do this? So as usual, we have to find the partition function, right? Partition function for such a system, because it's a quantum system, this formula is no longer valid, the formula that we used earlier. So this formula is not valid here since it's a quantum system. We have the original formula, which is just e to the power minus beta er, right, where this r is summed over all the distinct states of the system. And the energy, so in quantum mechanics, uh, this Hamiltonian, when it operates on the state of the system, it gives the energy of the system, right? So so what are the, you guys know the different, so let it denote by n. So do you guys know the different energy states? I mean, what are the energy of the different states of this quantum harmonic oscillator? You must have studied it in earlier quantum mechanics courses, right? It's given by this expression, right? Let me know if you guys don't know about this energy states. So just we will just put it here. So our partition function will become minus beta h bar omega n plus half, okay. And you know how to sum it. So this is just a this is just a geometric series, right? So you can further write it to simplify it, you can write it like this: n by 2 So this you can take out, and then you have sum over 0 to infinity e to the power minus beta h power omega n, right? And this is given by so this is a geometric series, so 1 minus power minus beta h power omega. So this is the partition function. Okay, and average energy, you know the formula. This is the formula for average energy. So now taking log of this uh, and then differentiating it, so let us do that. So we have beta so if you take log of this quantity, so you have two terms, sorry, so log of e to the power minus beta h power omega by 2 minus log of 1 minus e to the power minus beta h power omega, right? Or further you can simplify it, so this will be just minus beta h power omega by 2 minus, and this is this we will keep it the same. Okay, now differentiating it will give us h bar omega by 2, the first term, right? And the second term, this one, so this will come in denominator, and then differentiating above will give us first term will be 0, and the second term will be there is a minus sign here, okay, and then here again h bar omega e to the power minus beta h bar omega, right? Is it fine? So finally you will have h bar omega squared power minus beta h bar omega 1 minus beta h bar omega. Oh, sorry. No. This is. Oh, yeah, it is fine. Here, one should be there, right? Sorry. One should be there. This is plus 1 minus this. So, yeah. H bar omega by 2 Yeah, I've done a mistake. So let's not keep write like this. Yeah, this is now fine. So now it will be 1 plus e to the power minus beta h and minus e to the power minus beta h w, right? And this quantity, uh, this is 1 plus 2 will come here, right? Yeah. Yeah, so basically this will be the average energy. I don't know if I have done some mistake. Please check if this is okay. I think it's fine, but yeah, let's just give it a try yourself. Because yeah, it should be in terms of tan h, right? So I think this will give you this term in the denominator. What is tan hx? This is just e to the power, sorry, tan hx. Tan hx is sin hs by cos hx, right? Sin hx is e to the power x plus is it power minus x? Oh yeah, it is minus this, right? So mm, okay, let me try to do this again. I think I did some mistake. Till here it's fine. Till here it's fine, right? We just took the log of this exponential. It gave us minus beta h cut omega by 2, and then we have this term. Okay, this is fine. And then let's first take the derivative of this. So it will give us h bar omega by 2, and then plus derivative of this quantity, which will give us 1 minus e to the power beta h bar omega, and on the numerator we will have minus of the derivative of this quantity, which will again pull out a minus sign, so this will be plus beta h cut h bar omega, yeah, this is fine, and then e to the power minus beta h bar omega. Okay, so this is what sorry, h bar omega, yeah, sorry, yeah. So this is what you will get. Is it fine till here? Now if we take h bar omega odd, then you have half plus 2e to the power minus beta h bar omega divided by 1 minus the powers beta h bar omega. Correct? And then okay, so how can we convert it? Okay, so what we can do is uh, we can take out e to the power minus beta h omega by 2 as common from the bracket. That will or give us 1 in numerator. Okay, and here you will have by 2 divided by this, right? And then if you add this, what will you get? So you will get e to the power beta h omega by 2 minus beta I to the power, so this and this will minus beta h bar omega by 2, right, plus 2 e to the power minus beta h bar omega by 2, right? So finally you will have on the numerator you will have plus minus beta h bar omega by 2, right? And in the denominator you have, so this 2 we can take outside, and this we can multiply in the denominator. So you will have e to the power minus beta h bar omega by 2 plus e to the power uh, oh sorry, this is minus, yeah, sorry, this is minus, so this is minus beta h omega by 2. This one goes away, we multiplied it, right? Okay, so now you have the desired equation. So now you can write here, so I'm taking from here to here, h bar omega by 2 tan, this is not tan, this is cot, this is cot, right? Cot h beta h bar omega by 2. Yeah, so and then this you can write as 2 tan h beta h bar omega by 2, which is the answer. This finally. Is this okay? Somehow I messed up here, but yeah, finally we got the expression that we wanted. Sorry for the long derivation. So let me know if you did not understood any part of this. This was a easy. I mean, the concept he used here was easy. Just the calculation was a little tedious. So this was the last problem. Let me know if you have any question. Everyone understood? Okay, if you don't have any question or dot, then I'm closing the session. Wait. Dusasana Das. While taking h omega common, how you got 2 times power of e in the second term, where so okay ah yeah, you are right, you are right, you are right. This should not be 2 times. mm, yeah, this should not be 2 times, right? Yeah. It should not be 2 times. Otherwise, it will be 4 times here, because we are multiplying. No, I mean we are adding here. So yeah, now it's fine. Now it's fine. I did a mistake, but later on I did not realize that if you have 2 here, then this will become 4 here, right? You're right. Now it's okay, right? Dusasan, now it's fine. The final answer won't change. Yeah. Okay. So yeah, thanks for pointing it out. Yeah. Okay. Any other question or dot? If not, then let's close this session and meet again next Saturday. And you guys, please give it a try, this problem. Okay, and try to find these expressions. And if you will not be able to do it, then we will solve this in the next session completely. Okay. So thank you for joining. I'll end the meeting now. Okay. See you. Bye.